Good afternoon, my name is Alejandro Ruiz and I'm going to explain Chapter 8. Chapter 8 talks about addressing, and as we know, addressing is a key function regardless if the packet is to be sent to a host on the same network or in a different one. By designing and managing, it is easy to ensure that a network can operate effectively and efficiently. First, I will explain IPv4 address. Devices work with binary notation, it means zeros and ones, and the computers communicate using binary data. When we use a computer, for example, for writing something, we do it in a way that we can understand, but the computer must translate in order to understand it. The translation is done using ASCII. ASCII means American Standard Code for Information Interchange. IPv4 addresses are 32-bit binary numbers, but we see them as decimal numbers separated in octets and dots. IPv4 address has two parts. One is the network portion and the second is the host portion. The network portion will tell us the network from which the device comes from, and the host portion is a unique number to identify the host within the network. The bits within the network portion must be identical for all the devices that are on the same network. The thing that will identify them will be the host portion. When an IP host is configured, a subnet mask is assigned along with an IP address. Like the IP address, the subnet mask is 32 bits long, and the subnet mask signifies which part of the IP address is network and which part is host. The subnet mask is compared to the IP address from left to right, bit for bit. The ones in the subnet mask represents the network portion and the zeros represents the host portion. The subnet mask is represented in dotted decimals like the IPv4 address. Prefix length is another way of expressing the subnet mask. The prefix length is the number of bits set to 1 in the subnet mask, and it is written in slash notation followed by the number of bits set to 1. Depending on the number of hosts on the network, the prefix assigned may be different. There are three types of addresses within the address range of each IPv4 network: the network address, the host address, and the broadcast address. The network address is the standard way to refer to a network. The host address means that every device requires a unique address to communicate on the network. In IPv4, the values between the network address and the broadcast address can be assigned to end devices in a network. Broadcast address is a special address that allows communication to all hosts in that network. It uses the highest address in the network range. To ensure that all hosts in a network have a unique IP address, it is important to identify the first host address and the last host address. Hosts within the network can be assigned an IP within this range. The first host address will have all 0 bits except for the one in the lowest order. This address will always be 1 greater than the network address. It can be used for the router or default gateway address. The last host address, on the contrary, will have all 0 bits except for the lowest order, that will have a 1. It's always 1 less than the broadcast address. A device uses the subnet mask to determine what network address the device belongs to. This process is done through the logical operation AND. The IPv4 host address is logically ANDed bit by bit with its own subnet mask to determine the network address to which the host is associated. As a result of the ANDing between the address and the subnet mask, we will have the network address. When assigning an IP address to a device, we can do it in two ways: statically or dynamically. If it is done statically, the network administrator must manually configure the network information for a host. It's important to notice that they don't change very often and they are not normally reused. If it is done dynamically, it means that the assignation of the IP is done through DHCP, or Dynamic Host Configuration Protocol. This protocol enables automatic assignment of addressing information such as IP address, subnet mask, and default gateway. It is needed an address pool for addressing DHCP clients on a network, and when a client goes away from the network, the IP address returns to the address pool and can be used again for another client. There are three ways of communication in an IPv4 network, and they are unicast, broadcast, and multicast. Unicast is the process of sending a packet from one host to an individual host. The broadcast is the process of sending a packet from one host to all hosts in the network, and multicast is the process of sending a packet from one host to a selected group of hosts, possibly in the different networks. There are blocks of addresses that are used in network that require limited or no internet access. These addresses are called private addresses. The private addresses blocks are the ones appearing on screen, and these addresses should not be routed to internet. There are certain addresses that cannot be assigned to hosts. There are also special addresses that can be assigned to hosts, but with restrictions on how these hosts can interact within the network. The first one is network and broadcast addresses, also known as first and last host. Another special IPv4 address is the loopback address. The loopback address is a special address that hosts use to direct traffic to themselves. The loopback address creates a shortcut method for TCP or IP applications and services that run on the same device to communicate with one another. The range of this loopback address is 127.0.0.0 to 127.255.255.255. The third special IPv4 address is the link local address. This address is from 169.254.0.0 to 169.254.255.255. This communication is only suitable for communication with other devices connected to the same network. These addresses can be automatically assigned to the local host by the operating system in environments where no IP configuration is available. The next special IPv4 address is the testnet address, which block is 192.0.2.0 to 192.0.2.255. This is used for teaching and learning purposes. These addresses can be used in documentation and network examples. And finally, we have the experimental addresses, which is the last special IPv4 address. And this is the block 240.0.0.0 to .55, 255.255.254, and they are listed as reserved for future use. Currently, these addresses can only be used for research or experimentation purposes, but in the future they might be converted to usable addresses. The addresses are classified into different classes depending on the size of the network. We have Class A, Class B, and Class C. The Class A blocks are addresses that are designed to support extremely large networks with more than 16 million host addresses. They use the prefix 8. This means that the first octet indicates the network. Then the Class B blocks was designed to support the needs of moderate to large size networks with up to approximately 65,000 hosts. Class B networks use the prefix 16 to indicate that the first and the second octet indicate the network. Finally, the Class C blocks. This address space was intended to provide addresses for small networks with a maximum of 254 hosts. The Class C address use prefix 24. This means that they use the first, second, and third octet to indicate the network and only the last octet to indicate the host. The range of each IPv4 class is on screen. There are different organizations that are in charge of managing the IP addresses. The most important is IANA, or Internet Assigned Number Authority, and this organization manages the allocation of IPv4 and IPv6 addresses. Also, we have RIRs, or Regional Internet Registries, which manage the IP addresses within different continents. The major registries are AFRINIC, APNIC, ARIN, LACNIC, and RIPE-NNC. We can see them on screen, and we can see the region that they are supposed to manage. RIRs are responsible for allocating IP addresses to the Internet Service Providers. Most companies or organizations obtain their IPv4 addresses blocks from an ISP. An ISP will generally supply a small number of usable IPv4 addresses to their customers as a part of their services. So we know that to get access to the services of the Internet, we have to connect our data network to the Internet using an Internet Service Provider. So ISP have their own set of internal data networks to manage internet connectivity and to provide related services. Depending on the level of service required and available, customers are different tiers of an ISP. The ISP tiers are designated by a hierarchy based on their level of connectivity to the internet backbone. We have Tier 1, Tier 2, and Tier 3. The Tier 1 ISPs are the directly connected to the internet backbone. The customers of Tier 1 have high reliability and speed, but the drawback might be the high cost. Tier 2 ISPs acquire their internet service from Tier 1 ISPs, and they generally focus on business customers. The primary disadvantage of Tier 2 ISPs is slower internet access because they are at least one more connection away from the internet backbone, and they also have lower reliability than Tier 1 ISPs. Tier 3 ISPs purchase their internet service from Tier 2 ISPs. The focus of these ISPs is the retail and home markets in a specific locale. The customers of Tier 3 ISPs often have little or no computer or network expertise. Tier 3 ISPs often bundle internet connectivity as a part of network and computer service contracts for their customers. They may have reduced bandwidth and less reliability than Tier 1 and Tier 2 providers. They are good choices for small or medium-sized companies. The depletion of IPv4 addresses space has been the motivating factor for moving to IPv6. IPv6 is designed to be the successor to IPv4. IPv6 has a longer 128-bit address space, providing for 340 undecillion addresses. Due to the fact that both IPv4 and IPv6 addresses will coexist, there have been created several protocols and tools to help network administrators migrate their network to IPv6. They are the dual stack, which allows the IPv4 and IPv6 to coexist on the same network, the tunneling, which is a method of transporting an IPv6 packet over an IPv4 network by encapsulating the IPv6 packet inside an IPv4 packet, and the translation, which allows IPv6 enabled devices to communicate with IPv4 enabled devices using a translation technique similar to NAT for IPv4. So this means that an IPv6 packet is translated to an IPv4 packet and vice versa. IPv6 addresses are 128 bits in length and written as a string of hexadecimal values. Every 4 bits is represented by a single hexadecimal digit, for a total of 32 hexadecimal values. IPv6 addresses are not case sensitive and can be written in either lowercase or uppercase. There are different formats in which we can write an IPv6 address. There is a preferred format, which means that the IPv6 address is written using all 32 hexadecimal digits. There are some rules that will help us to reduce the notation of IPv6 addresses. The first one is omitting leading zeros. This rule applies to leading zeros, not to trailing zeros, otherwise the address would be ambiguous. The rule number 2 is using double colons, and this second rule helps to reduce notation by using a double colon, replacing any single contiguous string of one or more than 16 segment hextets consisting of all zeros. The double colon can only be used once within an address, otherwise there would be more than one possible resulting address. When used with the omitting leading zeros technique, the notation of IPv6 address can often be greatly reduced. This is commonly known as the compressed format. There are 3 types of IPv6 addresses: unicast, multicast, and anycast. The unicast is when an IPv6 address uniquely identifies an interface on an IPv6 enabled device. The multicast is an IPv6 multicast address used to send a single IPv6 packet to multiple destinations. An anycast is an IPv6 address which can be assigned to multiple devices. A packet sent to an anycast address is routed to the nearest device having that address. Unlike IPv4, IPv6 does not have a broadcast address. However, there is an IPv6 all nodes multicast address that essentially gives the same result. IPv6 uses the prefix length to represent the prefix portion of the address. IPv6 does not use the dotted decimal subnet mask notation. The prefix length is used to indicate the network portion of an IPv6 address using the IPv6 address prefix length. The prefix length can range from 0 to 128. A typical IPv6 prefix length for LANs and most other types of networks is /64. An IPv6 unicast address uniquely identifies an interface of an IPv6 enabled device. There are 6 types of IPv6 unicast addresses: the global unicast, the link local, the loopback, the unspecified address, the unique local, and the IPv4 embedded. The global unicast is similar to a public IPv4 address. There are globally unique Internet routable addresses. They can be configured statically or dynamically. The link local are used to communicate with other devices on the same local link. With IPv6, the term link refers to a subnet. Their uniqueness must only be confirmed on that link because they are not routable beyond the link. The loopback address is used by a host to send a packet to itself and cannot be assigned to a physical interface. The unspecified address is an all zeros address represented in the compressed format /128 or just 2 double colons. It cannot be assigned to an interface and is only used as a source address in an IPv6 packet. The unique local have some similarity to private addresses. They are used for local addressing within a site or between a limited number of sites. These addresses should not be routable in the global IPv6. IPv6 global unicast addresses are globally unique and routable on the IPv6 Internet. These addresses are equivalent to public IPv4 addresses. Currently, they are allocated with the first 3 bits of 001 or 2000:3. This is only 1/8 of the total available IPv6 address space. The global routing prefix is the prefix or network portion of the address that is assigned by the provider. Currently, RIRs assign a /48 global routing prefix to customers. The subnet ID is used by an organization to identify subnets within its site. And finally, the interface ID is equivalent to the host portion of an IPv4 address. The term interface ID is used because a single host may have multiple interfaces, each having one or more IPv6 addresses. IPv6 multicast addresses are similar to IPv4 multicast addresses. The assigned multicasts are reserved multicast addresses for predefined groups of devices. An assigned multicast address is a single address used to reach a group of devices running a common protocol or service. Assigned multicast addresses are used in context with specific protocols such as DHCPv6. 2 common IPv6 assigned multicast groups include all nodes multicast group. This means that a multicast group with all IPv6 enabled devices join, and all routers multicast group, which means that all IPv6 routers join. There are some messages that are sent when some error occurs. These messages are called ICMP. The purpose of these messages is to provide feedback about issues related to the processing of IP packets under certain conditions. The informational and error messages found in ICMP-v6 are very similar to the control and error messages implemented by ICMP-v4. However, the ICMP-v6 has new features and improved functionality not found in ICMP-v4. The ICMP-v6 includes router solicitation message, router advertisement message, neighbor solicitation message, and neighbor advertisement message. ICMP-v6 Neighbor Discovery Protocol includes 2 additional messages type: neighbor solicitation and neighbor advertisement. Neighbor solicitation and neighbor advertisement messages are used for address resolution and duplicate address detection. The address resolution is used when a device on the LAN knows the IPv6 unicast address of a destination but does not know its Ethernet MAC address. The duplicate address detection is used when a device is assigned a global unicast or link local unicast address, and it is recommended duplicate address detection is performed on the address to ensure that it is unique. This was Chapter 8 summary. I hope you understand it. Thank you for watching.